Hi, this is Alex Georgescu, and I'll show you how our collaboration of multiple groups at Northwestern University, MIT, and UC Irvine is working on accelerating materials discovery. If you want to learn more about my work or get a clickable version of this poster, you can scan the QR codes here. Our workflow here shows our approach to materials discovery, from building our domain knowledge to rapid filtration of materials, optimization of certain materials classes, to even new synthesis recipes for the materials we've discovered, or the materials we're proposing. In this work, we're focusing on metal insulator transition compounds. So these MIT compounds show a transition from an insulating low temperature phase to a metallic high temperature phase. There's a dearth of materials with a sharp transition that operate above room temperature. As a result, VO2 here is the most used material. One of the main goals of our collaboration is to discover new materials that are maybe even better than VO2, as well as show how machine learning can accelerate materials discovery. Density functional theory calculations are performed as part of the discovery cycle, and we note that these are high fidelity, so not high throughput calculations, to correctly evaluate things like energetics, band gaps, and synthesizability of the different materials, as well as their transition mechanisms. In collaboration with Elsa Olivetti's group using natural language processing and human verification, so reading some articles, we've built a first database of MIT compounds and made it publicly available. You can access it from the clickable version of this poster. On this database, we've built a tree-based machine learning classifier model to A, identify relevant features that indicate whether a material is an MIT material or not, and B, discover new potential candidates, and we've proposed some new materials for experimental validation. Also in collaboration with Elsa Olivetti's group, for each material we propose, we've also provided synthesis pathways to give our experimental collaborators as they approach the new materials. Finally, in collaboration with the groups of Wei Chen and Dan Apley, we've identified new compounds within certain materials families, namely lacunar spinels and Wilson-Popper perovskites. Bayesian optimization and mixed variable, latent variable Gaussian processes greatly reduce the number of materials that we need to simulate before finding the Pareto frontier. Also, they allow us to gain some insight into the physics of the materials. Some of the proposed materials are undergoing experimental validation in Divine Kuma's group at North Carolina State University. You can find all the tools we've built as part of this project, as well as papers, in the clickable version of this poster. Thank you.